This is to introduce you to the total synthesis project that you will work on for the remainder of the semester. What is a total synthesis? A total synthesis is a stepwise synthesis of a very large molecule, and this often includes a retrosynthetic analysis. These are done all the time with natural products. So these products might have been extracted from several tons of marine sponge to give us a couple of milligrams, and then chemists will look and try to decipher the structure using spectroscopy of different methods. And then once they find the structure, they look for activity. So some of these compounds might be potential anti-cancer compounds, and then they have to find a way to synthesize it. So all of these compounds that are on this slide are natural products that have been found in sponges and have later been synthesized. The guidelines for your synthesis is that all of the starting materials must be commercially available. That means that you can't make up chemical compounds. Once you find a structure that you want to use, you can use SciFinder in order to determine if it is commercially available or not. There's no price limit or minimum or maximum. So if you find a starting material that costs $2,000 for 1 gram, you can still use that. There's not a price limit here. The materials that you use for your synthesis must have 6 or less carbons and can contain no more than 2 functional groups. For example, if you wanted to start with phenol, you can start with phenol because it has a 6-membered benzene ring, which is a functional group in and of itself, and there's also the alcohol group there. But you can't start with a molecule that has 2 functional groups on them. You can use any reactions that you learn from chemistry, from Chem 225 or 326, so organic 1 and 2, or you can use any literature. If you do find some reactions in SciFinder, they must be referenced in the ACS style format. And be creative with your synthesis. For your process of doing this, you have to do a retrosynthesis, which is working backwards. And in order to do this, you want to look for disconnections where there are functional groups. You want to also keep track of the carbons that are added or that are needed. Along the lines of looking at your carbon numbers or keeping track of them, I just want to point out a couple of common synthesis mistakes that students make. And one of them is not counting the number of carbons. You might start with 6 carbons and magically a 7th carbon appears, or you can lose carbons along the way. So make sure to keep track of your carbons in your molecule. LDA removes a proton at an alpha carbon of a carbonyl, so you can't use it if there's not a carbonyl present. You also do not want to use it to try to do an E2 elimination reaction. RMG is not a Grignard reagent. A Grignard reagent is RMGBr. So make sure that you are using it correctly. If you attack an alkyl halide with a Grignard reagent, that Br goes away. So if you have an MgBr, we're going to react it with R prime Br. Your bond that you're forming is between R and R prime. So this Br is now gone. So that's another thing that you want to remember with Grignard reagents. Make sure that you are checking for other functional groups in the molecule. If you are trying to do an oxidation using KMNO4 of this compound here, and you're trying just to oxidize that alcohol, you want to remember also that KMNO4 can oxidize benzoic hydrogens to give you benzoic acid, and you're not going to get your desired product. So make sure that you are checking for other functional groups in your molecule. If you are looking to use lithium aluminum hydride to reduce an ester and you have a ketone present, remember that lithium aluminum hydride will reduce everything that has a carbonyl. So it will reduce this as well. So you end up getting the 3 alcohols instead of just the 2 here. In order to reduce just the ester, you will need to protect that ketone first. Also remember that nitriles can get reduced by lithium aluminum hydride, just like an amide, an aldehyde, a ketone, and an ester. You cannot do SN2 reactions at sp2 carbons or at tertiary carbons. It's sterically hindered, and sp2 carbons are not conducive to SN2 reactions. Likewise, you cannot try to do an SN1 reaction at a primary carbon because that's not a stable carbocation. And lastly, you cannot do a Friedel-Crafts reaction with strong electron withdrawing groups or strong electron donating groups. So if we have a nitro group on the benzene ring, you cannot do a Friedel-Crafts, and you can't do one with an OH or a phenol. So in your retrosynthesis, it doesn't have to be overly detailed. The molecule that is the target is on the right upper corner there, and you can kind of see the little breaks that I've made in this molecule where the red arrows are indicated. And this is not a stepwise retrosynthesis. So you don't have to show every single step going back. This is just kind of the major pieces that you can see that the molecule breaks down to. So at the end of the day, the molecules that I'm using are something like this and this over here, which are affordable starting materials that have less than 6 carbons. When you're doing a retrosynthesis, I mentioned breaking apart molecules where functional groups are present. So I might choose to make some breaks where the carbonyls are, or next to the carbonyls, or where there's an alkene. You don't want to get trapped into just making these things separate pieces, such as in this form here. As standalone pieces, we have an aldehyde, cyclohexanone, and another ketone, and these are all electrophilic, and we can't put them together because we need a nucleophile and an electrophile. So don't hold yourself into just making the bonds and trying to connect them with magic. Use the functional groups smartly. So I have this acid chloride here, which is electrophilic. I know that I can use the alpha carbonyls in order to do the reaction. And then I can use that alpha carbonyl chemistry to do an addition at this 4 position to do a Michael addition. So try to make your functional group breaks make sense. And then you have to think about the forward reaction and how you want to connect the pieces together. So for me, if I wanted to put this molecule together here, I'm going to use the Robinson annulation, which puts 2 pieces together. I may need to alkylate this first because this has 7 carbons. And then I can do a Michael addition followed by the aldol reaction to get that Robinson annulation. I can use LDA to form a bond at the alpha carbon and then add that to the acid chloride to get that compound structure there. Other things to think about in your forward synthesis. Are you adding the correct number of carbons? Make sure the number of carbons that you're starting with matches what you want it to end with when you're adding things along the way. Check to see if you need to use protecting groups. We saw that with an ester and where we had to protect the ketone. You also want to see if the reaction that you're trying to do is going to affect other functional groups. So if you're using H2 palladium to reduce an alkene, make sure that there's no carbonyls present that could also get reduced or any alkynes there. Can your reaction be done in less steps than you have it? So we've already seen this in the more recent chapters where we can put pieces together more quickly than we did using just Chem 225 or Organic 1 reactions. So look for quick reactions or even use SciFinder to see if you can cut out a lot more steps. Is your reaction going to result in multiple products? If it is there a way to avoid it? You also want to make sure that your reaction is giving you the correct stereochemistry if that's an issue. So if you are getting cis, do you need to be getting trans? Is it going to give you a mixture? Also make sure that you're getting the right regiochemistry. So a Markovnikov addition versus an anti-Markovnikov addition. And then also check to make sure you're doing the steps in the right order. And we saw this was especially important in the aromatic electrophilic substitution chapter. So you may not have used SciFinder recently, but make sure that you do look into that to try to find reactions. You can use this to find efficient reactions that you've not heard of before. So in order to do this, there will be a video posted on how to use SciFinder again, but just briefly here, you can go to the Explore option and search for a product. And then this might be something that you want to synthesize, this fragment right here. A way that you know how to put an alcohol on a benzene ring is by bromine, which uses harsh heating conditions. And maybe that will cause you to lose your acetal. So you want to find a different, more gentle route. So you would just enter in what you want as your final product there from the beginning material, and here are some milder conditions to do that chemistry if you can get that bromine put on there. And so if you're moving in your forward synthesis, this is a different molecule, but you start with catechol, which has 2 alcohols here, bromine and FeBr3. We add that bromine. We can put this acetal group on here, and that reaction should also be referenced because that was not one that we learned in our class. And then this is the step that was referenced using SciFinder. This is this catalyst at 80 degrees to put the alcohol there without having to heat it to 350 degrees. The other thing with this, with the BR, when we learn how to use this, you could either use the 350 degrees or have an electron withdrawing group, ortho or para, but we have 2 electron donating groups here, so this kind of saves us a step as well. And then you can go on to your next step. This TBS chloride is a protecting group for alcohols, so that's protecting this here. And we need to protect that alcohol because we're using this BR and turning it into a Grignard reagent. And if you have a Grignard in the presence of an alcohol, that can just deprotonate that alcohol, and then your Grignard reagent is dead. So this would be another chunk of the molecule. So we react the Grignard reagent, so you can make it, but it's also commercially available. So that's something that you want to look for as well. If you don't need to worry about making the product, then you can buy it, then that will save you some steps as well. So I'm adding these 2 molecules together, working it up with water, and then adding fuming sulfuric acid in order to have that blocking group installed there. And then I have the blocking group, which will allow me to put a group nitro. I oxidize my alcohol and then use LDA in order to do an Michael addition to this compound here. It probably would have been a good idea in this particular reaction to use the storic enamine synthesis in order to make that a better nucleophile. That would be an improvement on this synthesis. All right, so once we have that molecule together, I can oxidize my aldehyde to the carboxylic acid and then use the acid chloride or thionyl chloride to make it the acid chloride. And then I can put that together with my part A of the molecule, and that will fuse these 2 chunks together. And then I'm going to add thionyl chloride, or I'm sorry, a dithiane, in order to protect both of my carbonyl groups. And once those are protected, I can use zinc HCl in order to reduce my nitro group, use sodium hydride and make this nitrogen more nucleophilic, which can then attack the epoxide. I also deprotected my carbonyls in the prior step there. And then to finish up the synthesis, I oxidize that to the carboxylic acid, make it the acid chloride, deprotect my TBS group, and then make another ester here. And that is the end of the molecule. When you're presenting your synthesis on a poster, you don't need to have a typical sections that you would normally have on a poster. So we don't need an introduction or a methodology. You just have to have your retrosynthesis, which again does not need to be step by step. It just can be very general, and then have your synthesis on the poster. There will be examples of some syntheses on Moodle so that you can see kind of what you should be aiming for. The size of the poster doesn't matter because we're not actually going to print them. We'll just be saving them as a PDF, but it should be legible. It should have a logical flow. The font should be big enough to read without having to zoom it in to 300%. It should look visually appealing, so make sure that you're aligning things, boxes, and your fonts aren't all kittywampus. And then make it look like you didn't just slap it together at the last minute. Your structures need to be drawn out using either ACD Labs, which is an app that you can use on your computer, or a program. You can draw the structures in SciFinder and snip clip it, or you can use a program called King Draw. So you will not be allowed to just draw your structures on random pieces of paper and submit them on the poster that way. They need to look put together. So take some time to draw the structures using any program. There's other probably free drawing programs out there, or some with free trials that you can try out as well. but the structures need to be drawn out. Look at the examples on Moodle in order to see what the expectations are for your structure as well as for your synthesis.